and final example in this section. Let's consider this series, the sum from n from 1 to infinity of 1 over square root n. Does this converge or does this diverge? So the first thing to note is, well, we might consider the limit as n goes to infinity of the nth term here, and this is going to be 0. And so we might be tempted to look at this and say that, oh, if we took the limit of those individual terms and got something other than 0, then we would know the series diverges. It might be tempting to look at this, see that we do get 0, and conclude that the series does converge. However, that's not applying this theorem in the right direction. This just says that the limit of the individual terms is not 0, this overall series diverges. It does not say that if the limit here is 0, then the series does converge. And so as it turns out, this series does diverge, and we can think about that by just considering the sequence of partial sums. So S of n is equal to 1 over square root 1 plus 1 over square root 2 plus 1 over square root 3 plus ... plus 1 over square root n. And there's n terms here. And we can say that this is, so 1 over square root 1 is bigger than 1 over square root n. 1 over square root 2 is bigger than 1 over square root n. 1 over square root 3 is bigger than 1 over square root n. And so why do we do this? Well, we have, this is n copies, because there were n terms to start with. This is n copies of 1 over square root n here. So n divided by square root n is square root n. So overall, this proves that S sub n is greater than or equal to square root n, and because the limit of square root n is, as n goes to infinity, is infinity, that shows that the sequence of partial sums diverges as well. So we can conclude here that our series diverges even though the limit of the individual terms is equal to 0. So make sure that you keep that straight.